Standard machine learning architectures process all of their incoming data by forcing it through rigid, predefined computational pathways. These models rely on an external parameter known as a fixed context window. This architecture forces the network to allocate identical computational effort across an entire layer, regardless of the data it is processing. This creates an immediate inefficiency. A simple, unambiguous input receives the same processing depth and node allocation as a highly complex one. Standard binary or scalar activation functions are responsible for this. Once a mathematical threshold is crossed, they trigger forward propagation indiscriminately. In these standard models, the attention size is predefined by the architect before the operation even begins. This fixed matrix becomes a computational bottleneck when local ambiguity exceeds that pre-allocated window size. The query overflows the capacity, and the unresolved data tangles. To resolve this, we have to look past external architectural parameters and focus on internal node-level logic. We can construct a homo-iconic system where computation is dictated by the internal relationships of the data itself, rather than arbitrary external bounding boxes. Efficient computation requires a network that scales its own compute based on the level of local ambiguity it detects. Attention is not a fixed architectural constraint. It is an emergent property generated by the data during the operation. This requires moving to a discrete, directional routing mechanism at the level of the single neuron. This formula defines the ternary activation function. Activation in this system is expressed as a discrete ternary value. This ternary value dictates the precise directional flow of computation as it navigates the network topology. Every activation triggers a structural routing decision made by the neuron itself. These three states represent three distinct actions: total inactivity, vertical propagation to the next layer, or lateral delegation to peers. Hard-coding these routing options into the activation function eliminates the need for an external attention hyperparameter. Granting the neuron routing autonomy allows the network layer to self-organize around the incoming data. This state of lateral delegation turns the neural layer from a rigid feed-forward pipe into a dynamic problem-solving graph. We can isolate a single neuron to analyze the micromechanics of these discrete states. State 0 is strict inactivity. The neuron detects no relevant data, transmits nothing, and triggers no subsequent operations. Now we introduce a simple, unambiguous input. When the node reaches sufficient resolution, it triggers state 1, vertical propagation. The node fires a vector we call R. This represents a resolved calculation ready to be absorbed by the next hierarchical layer. Triggering alpha equals 1 halts local processing immediately because the specific problem is solved. For simple queries, the network resolves the input using exactly one node, with no additional computational overhead. States 0 and 1 represent the extreme ends of certainty, absolute irrelevance or absolute resolution. However, if a single neuron processes an input but fails to reach sufficient resolution to calculate R, the system must handle the ambiguity. Standard binary systems fail here by forcing an unresolved state vertically, polluting the subsequent layer with low-confidence data. Ternary logic offers a different path. The neuron recognizes its own insufficient resolution, halts upward movement, and enters state 2, lateral propagation. It emits a K-vector, or a carry. This is pending information that circulates laterally within the same structural layer. The receiving neuron incorporates this data, updates its internal state, and evaluates the new combined relationship. This second neuron now faces the same ternary decision. It must select state 0, 1, or 2. If that combined data remains ambiguous, the network expands its footprint. The second neuron generates a new K-vector, passing the unresolved calculation laterally. This process delays vertical propagation until the collective lateral pool possesses enough localized information to solve the ambiguity. The lateral carry functions as a dynamic delegation protocol, allowing local nodes to recruit peers until they reach a vertical result. When we observe an entire horizontal layer, these individual decisions create a complex topology. Multiple inputs hit the layer concurrently. A simple input registers alpha 1, firing its R vector upward. A moderately complex input links 3 nodes laterally before firing upward. An ambiguous input triggers larger recruitment, branching out to 15 nodes before resolving. There is no uniform processing structure forced onto these disparate inputs. The carry chain can extend as far as the data requires. The network evaluates its exact computational needs, operation by operation. The layer stops expanding the lateral chain the moment coherence is achieved. The data gathered from that lateral pool is then compressed into the final R vector and sent to the next layer. The shape and size of that lateral footprint is constructed by the data's internal structural needs. Computation is defined entirely by the boundaries of the carry chain. This formula redefines attention within a ternary homoiconic system. Effective attention is the physical footprint left behind by the lateral K vectors. Attention becomes an emergent boundary defined by the specific complexity of the problem. Transitioning to discrete ternary logic ensures the model constructs a bespoke attention window for every operation, allowing computational resources to scale according to the specific needs of the data.